I don't think we need to spend much more time with the series ones. I think you guys have a pretty good handle on that, but that's not where this is going to end, of course. So let's take a look at a couple of other things. And there's more to this than what I've been talking about. Right now I've been focusing on the dielectric part, but we're going to only do that for a little while today. So this is going to be a little different. I'm going to draw this in a way that's not particularly efficient, but I think it'll be clearer what's happening. All right, so C1, C2, voltage. Now, I want to play the same game as yesterday. I want to take a dielectric and insert it into one of the capacitors and talk about how that's going to change this system. In some ways, this one's not going to be as difficult, but just be patient. I think you're going to see something that's going to be kind of tough here in a minute. So let's start with the simple. If I take the dielectric after the system has reached a steady state, you're going to start hearing me use this word too. Start picking up on it. The steady state condition and the time zero condition. Start picking up on those two phrases. Right now, we're assuming all this happens instantaneously. And I have a circuit like this. I say the capacitor is uncharged. I close the switch, and suddenly the capacitors are charged. This does not take place instantaneously. It takes time for this to happen. By definition, we're going to find that it's going to take an infinite amount of time to charge a capacitor. But of course, as we talked about, infinity isn't as long as you think it is. It tends to be just a few milliseconds here. But in the life of a circuit, that can be a very long time. When we close this circuit, right now, we're talking about comparing the time zero state of the circuit with the steady state. In every example we've done, we've just assumed the moment we close the switch, the capacitors are charged. And for the time being, we're going to assume they are. But when I refer to the steady state, I am referring to the state of the circuit as it will be in the future and is unchanging. So the steady state condition for our circuits generally is what happens after you wait long enough for all of the things in your circuit to settle. So if you make a change to your circuit, open a switch, connect something else, push in the dielectric or take out the dielectric, any of those things alter the system. It takes time for the system to accommodate that change. So when we say the word steady state, we're talking about getting back to the state of the system in which things are not changing in the system. So if we assume that we've closed the switch and the system has reached its full charge, that's saying the same thing as saying the system has reached its steady state condition. So right now, both capacitors are fully charged. And you should also know then that they have different amounts of charge in this case because they are in parallel, but they have the same voltage. Correct? You guys remember that? Parallel, this part's not going to be so terrible. Because if I just add the dielectric here, I change just the one capacitor. Because they're not in series, this one has a direct connection to the battery and therefore has a direct connection to the potential difference. Potential difference isn't going to change, but because the capacitance increased, it just pulls more charge directly from the battery just to this capacitor. It doesn't affect the whole system like the two in series did. Does that make sense? Everybody understands that, right? And the same rules are going to apply here as before, right? This is going to increase the capacitance, therefore it's going to increase total energy being stored, because it's going to increase the amount of charge in that capacitor. All of those things are true. So the parallel part isn't what's particularly interesting. What's interesting is considering what happens when you have a charged system, let's say the system is charged, and then I isolate the system. Now things are a little bit more challenging. I want you to think about this, maybe have some conversations at your table for what happens if I take this dielectric and put it into the circuit now when the system is isolated. Think about it for a minute. Maybe toss around what you know can change and what you know can't change. And if you want, this might be a case where it might be better if maybe we threw a few numbers at it so that you have some things to bat around. So let's say that this is 12 volts. Let's say, and these have to be different in order for this to make a significant impact. So let's say that we've got a 2 farad and a 4 farad capacitor. And let's say the dielectric constant is 2. Okay? So let's do the first part of this. Let's figure out the initial charge, initial voltage, all that stuff. That one should be pretty easy. So just to make sure I have everybody paying attention, you know I'm going to pick on somebody to tell us what the initial charge and the initial voltage is. And we'll do that in 5, 4, 3, 2, 1. People still working, it looks like. Giving you a chance to confer with your friends before I just call somebody out in the middle. All right, so that's been enough time, I think. So Nick, do you think you have an answer back there? See you guys working it out.
24 coulombs and
24 coulombs and 48 coulombs. Who backs them up? And both 12 volts. Excellent, excellent, excellent. All right, so that's our starting state. We are going to isolate the system, and then we're going to place this dielectric between the plates. Maybe. Now, talk at your table. See if you can figure out what you think's going to happen. It might surprise you. So again, just like in the series one, when we isolate a system of capacitors, we are fixing in place the total amount of charge that's been separated. So in this case, you're going to have 48 plus 24 coulombs of charge. That's what you have to work with. So 72 coulombs of charge. Now you have to deal with how it redistributes itself. And there are some other things to keep in mind. We know that this capacitance changes and goes from 4 to 8. Right, that has to be true still too. There's one more thing that has to be true. Anybody else have a thought about what it's got to be? What's that? There will be a ratio that's going to be changed because the ratio changed. But there's something here that goes way back to when we were first solving circuits that has to remain the same. Yeah, I don't know what the new voltage is, but whatever the new voltage is has to be the same on both capacitors. It has to. They're in parallel. If there's a change in the voltage on one of them, if the voltage was different between these two, that would drive charges from one to the other. The reason the charges move is because when you suddenly change the capacitance of one of the capacitors, you're changing its voltage. And that's going to cause charges to move from areas of high potential to areas of low potential. And as the charges move, they change the potential. So you have pieces of information now, right? We know the total amount of charge is 72. We know that we're going to have the same voltage. Is that enough for you to figure out how the charges will be distributed and what the new voltage is? Try it. Get a number. You have lots of info here. So, again, I don't really think I have everybody paying attention. So let's get everything together. We know the total charge has to be 72 coulombs. And charge is the product of capacitance times voltage. So the voltage has to be the same for both of them. So just take these two capacitances.
You can do it. I believe in you.
It's got to be 2 farads times the voltage across that capacitor plus 8 farads times the voltage across that capacitor. It has to equal the total amount of available charge. Now this gives you the voltage, of course, 7.2 volts. But once you have the voltage, you can also find out how the charge has redistributed itself across those capacitors. We good? Now, they can be worse than this. I want to be really clear, they can be worse than this. But there are some things that you should probably bear in mind. No matter how complicated it gets, and they can get more complicated. No matter how complicated they get, there's some obvious rules that have to stay in effect. And one of them is clear. Charge is finite. Once you isolate it, the charge is going to be the same. It's got to. What becomes more challenging is when you suddenly start getting into an area where you can't tell what's in series and what's in parallel. So consider these two examples as what I mean by that. First, I'll try and draw this neater than I did last time, but no guarantee. Having more than just 2 can clearly add an issue. So 2 farads, 4 farads, 6 farads. This one's still not going to be terrible. It's going to obey all those same rules. It's just more stuff here. So if I give it 12 volts and we use the same dielectric, it doesn't really matter where you put it. Right? The activity is the same. There's going to be a fixed amount of charge here. Once you know the total amount of charge, you're going to have a simple process of distributing that charge because the totals have to add up to be whatever the total is before you put the dielectric in. So don't be scared away because there's a bunch in parallel. The rules still have to stay the same. They all still have to have the same voltage when you're done. Where it becomes hard is something like this. Now you should be able to solve this circuit. I suspect it won't take you very long to do so. So take a moment and solve this circuit. Find the charge and the voltage across all the elements. I want to see it in your notes. This one should be easy. So 60 seconds. Huh? I can't hear you. All of it. Oh, I don't care about this. I don't care about this one. That one was just to show you that if you have a bunch, it's still going to obey the same rules. I want to talk about the right one. Sorry. But I saw a lot of good stuff, so good. 12 volts, right? And how did the voltage divide itself up amongst the 6 and the 3? Yeah, we just did it, right? So 4 volts and 8 volts. All right. So we're going to isolate the system after it's reached its steady state condition. So my 3 farad here, my 4 farad here, but the dielectric is going to be put here. Now I want you to be careful. You know how much charge was separated in this circuit. Did you add up all 3 sets of charges for the total charge in the circuit? I'd be really careful about this, and I'd pay careful attention. We know that this is 48 coulombs of charge here, correct? And we know that there's 24 coulombs of charge here and 24 coulombs of charge here, correct? So is the total charge in this circuit 24 plus 24 plus 48? It's not. Remember, that piece is still got charge that's not going to be able to leave, right? In that middle. You have to treat this as though it'll only have one amount of charge. So the total charge in the circuit is just 24 plus 48. I don't know why I erased the middle one. Let's go with this one. That's the total available charge to move around. But a shrewd person is going to ask me a question that, aren't they all in series now? Right? The moment I isolated them, doesn't it look like they're all just in series? How does it still know that it's up 2 parallel legs? Like, why are we treating it that way? And there's a good explanation as to why we do. And I want you to hear this closely. This plate is positive, this plate's negative, this plate's positive, this plate is negative, right? Because of the way it was connected here. This plate is positive and this plate is negative. When they're in series, the plates alternate, positive and negative. But these 2 parts were connected to a potential difference. So this whole area here is all positive charge, all repelling. This whole area here, all negative charge, right? All repelling. When I do that same thing here, that's not true, right? I have positive and negative separated, so they can flow back and forth and equalize. It can't happen on the other parts. So you still treat it as if this is in parallel with this because of the way the charge is distributed. Everybody follow what I'm saying? That's how you know what's in series and what's in parallel. Just treat this side as if it's a parallel side, and you will be fine. Consider what's going to happen to the equivalent capacitance. Tomorrow, I want to consider this kind of thing. What would happen if we tried to pull a plate away from another plate? Or maybe try and push them together? What kinds of effects would we have? All right.